Can everyone see my screen?
Yep, looks great.
So thank you everyone for giving me the chance to speak today and share my research. So I'd like to give you a quick introduction to the project and then tell you about some of the measurements that we've taken and discuss the results. So presently, over the last 2 to 4 years, there's been quite a number of European projects to try and increase the measurement capability of particle counters to tighten the legislated limits. A couple of these were actually undertaken at Johnson Matthey, the DEEPA project and Paragen, and the main desire has been to reduce the size cutoff from 23 nanometers down to 10 nanometers. The reason for this is particles in the smaller size range are considered to be more harmful to humans. So that does bring the question of why it was 23 nanometers to begin with, which was more to do with the stability of the measurement and the repeatability that could be seen. And also when the legislation was brought in to control diesel emissions, the average size range is above that limit anyway. But in the future, with GDI, there are more questions around the typical mean diameter. So the DEEPA project, as I mentioned, was a project to understand particles from a improved efficiency diesel engine from 10 nanometers onwards. And some of the results from that project mirrored similar results from a few of the others, which showed that particles in the 10 to 23 nanometer range were captured by filters quite efficiently, because filters do operate very well in that diffusion regime towards the smaller size range. But what we did find was quite a repeatable high concentration particle emission that we believe to be volatile, which was to do with the way that we was measuring the particle emissions. So at the laboratory at Johnson Matthey, we were studying the vehicle emissions on a chassis dynamometer, and we was measuring through a constant volume sampling tunnel similar to that of legislation, but including testing using a solid particle counter. We also used the combustion DMS 500, which uses electrical mobility measurements to detect both the size and the concentration of particles. And we can gain quite a lot of useful information from that, but there isn't a volatile removal system in the version that we was using. We was relying on the equipment's post-processing to understand the composition of the particles. So when we had seen that consistent volatile particle emission, we decided to study it, and we took a few different methods to do that. So we tested using a catalytic volatile particle remover, which is what is looking like will be included in future legislation. We manipulated the drive trace, which was the worldwide light duty test cycle, to understand under what conditions this would be generated and released. And we tested from multiple sample points in the vehicle. Some of the more recent testing has started to raise issues with constant volume sampling tunnels due to the way that the exhaust gas is diluted, and the possible formation of more volatile or nucleation mode particles due to that system. So there is talk about measuring from the tailpipe, so we wanted to compare those two systems. We also took some samples from within the exhaust and from the engine oil itself that was on the vehicle, and we took those samples before the release event. And we also investigated the selective catalytic reduction system, which uses urea injection to treat NOx emissions. And we also replaced the lubrication oil with a zero or very low sulfur formulation supplied by BP. So the confirmation of the particles being volatile was performed using a diesel oxidization catalyst that was heated. It was a purpose-built catalytic volatile particle remover by the University of Cambridge, and that consistently did show removal across a number of DMS units, which were measured in tandem, and also using a TSI CPC, which did not have the standard evaporation tube that legislated equipment would use. And we also demonstrated that if the vehicle only was driven at high speed, then the volatile emission would not occur. And we demonstrated that for this emission to occur, the vehicle had to be driven at low speed, and there seemed to be some correlation to the distance driven at low speed urban driving to the particle emission, but with the volatile emission being very dependent on dilution, this was quite hard to quantify. But we could demonstrate that with only high speed driving, there was no emission that could be detected. And then measuring from different sample points on the vehicle to try and understand whether it was just a artifact of the dilution tunnel, we found that we couldn't measure directly after the vehicle's catalyzed soot filter or DPF, and this is likely due to catalytic reaction with the sulfur to keep it in the gas phase at this point is likely nucleating further down the system, which is where we was measuring it at the tailpipe, but at a much lower concentration than what we've seen at the CVS tunnel. It was not just a shift in concentration and particle size, it was the mean diameter didn't really change, it was just a increase in concentration that was seen. The characterization that was undertaken was performed directly after low speed sections. So samples were taken from the disassembled exhaust system, and TGA and SEM showed sulfur and ammonia. The ammonia was likely from the rear injection system, and that has been known to cause similar volatile events. So we wanted to look into that and see whether that was the cause, and we wanted to discover the source of the sulfur. So we decided to study the engine oil to see whether it was a particularly high sulfur blend that was supplied from the factory, or whether it was quite a low sulfur blend. And we found that it was very low sulfur. Low sulfur oils are usually below 4,000 ppm. But the measurement system that we used wasn't ideal. This is going to be repeated on the samples that we have once we can send the samples away from testing after the current restrictions are lifted. So the ammonia injection system, as I mentioned, to remove any contamination and source of ammonia, the urea injection was removed and any pipe work or catalysts that will have been in contact, and this had no effect on the particle emission. So we demonstrated to ourselves that the urea injection or ammonia was not the source of this particular emission. And then using a sample of oil supplied by BP, we received a sample that was proven by them to be less than 25 ppm of sulfur using ICP, and we could not replicate the particle emission event that had been extremely consistent over the last few years. So this really did show that this was the source of this particular volatile emission. And to conclude, the particle emission that we measured, we demonstrated required low speed driving, urban driving, quite gentle low pressure combustion, and this buildup of sulfur compounds that we found in the exhaust system and most likely inside of the particle filter as well would then be released. The particle emission was shown to be volatile, and because of that, it's not something that would be currently measured using Euro 6 legislation testing methods. The particle emission was not detected directly after the filter. I have spoken with other people who've measured similar events, and they have not been able to measure at the tailpipe in a lot of instances, and I believe other people speaking today may be mentioning similar things like this because there is a desire to move away from constant volume sampling testing, but I don't think that's confirmed yet. The deposits of sulfur that we found, we traced the engine lubrication oil. We also tested the fuel that was being used, which was found to be very low sulfur, commercial grade diesel. And this low sulfur formulation of oil that we tested removed this emission completely. The selective catalytic reduction system didn't play any role in this particular emission. And finally, we do think that events like this may be occurring on other vehicles, but may be released during regeneration events where the filters are heated to combust any stored soot. It would make sense that if the sulfur is collected in those filters and they're only released during those events, this would be seen less during normal testing that's completed. But I believe future legislation is looking to include regeneration events as well, so that would give more indication of that. So I do want to take the chance to thank everybody that was involved, including the deeper project members that also supported this work, Jeremy and David. There's the entire vehicle testing teams and maintenance teams here at Johnson Matthey, along with the characterization team. And then Dr. Adam Boyes, who's hosting this event, was my supervisor through most of this work. And I'd like to thank David and Frank at BP who made and supplied the sample for us. And any questions can be directed to us and BP and Adam. Thank you all very much for listening, and I hope anybody has any questions.
Great, thanks so much, Stephen. Yeah, we have time for a couple of questions, and so James, you were the first on the trigger. So if you want to unmute yourself, or I can unmute you as well, the floor is yours.
Hey, can you hear me? Hello?
Yes, we can hear you.
Yep. Excellent. Sorry. Yeah, it's very interesting stuff, that. In terms of regulation, how much of these would be captured by the regulations concerning VOC emissions? Because you'd think there'd be a kind of continuum going on between the volatiles and the kind of volatile particulates and the volatile gases.
Because the levels were extremely low, because the particles were of such a small diameter, if you look at them as a high concentration event, the number wise is considerable, but the actual mass is extremely low. So the largest events are probably less than 1 milligram total. And over a complete drive cycle, it's a very, very small amount. That added to the difficulties in capturing and understanding the particles.
Good, thank you. And next up we have Matthew Berry has a question. Let's see. There we go.
Ah, there we go. I'm unmuted. Thank you very much. Okay, I'm from 3.x, and we produce the parsync, which when we're working down in the very small particles, we use ionization detector. And we've been testing at JRC and West Virginia University, where we are seeing with our ionization sensor that we detect all particles, including volatiles, down to very small size. We were in contact with Adam Boyes, who recommended us to Catalytic Instruments in Germany, where we're now testing at West Virginia University the catalytic instruments as well. And we're seeing that it's possible with and without the catalytic instruments device to detect purely volatiles that are present in the exhaust stream measured at the tailpipe, which I believe you were mentioning in your presentation.
Yes, yeah. I know there has been some discussion that the measurements would only be captured by CVS, but
Hello?
Oh, sorry, it looked like it muted me. Sorry. Yes, we did demonstrate the measurements at the tailpipe. There's been a lot of discussion about volatiles only being a problem the tunnel where the dilution causes very high concentrations to form. But the fact that we showed it at the tailpipe as well does make us believe that this could be a condition that would occur in the real world, and at particularly high traffic areas, if there is a constant stream of these high concentration particles, they could build up to a point where they would stay around in the atmosphere in that area.
Yeah, when we tested a diesel vehicle with DPF at JRC, we saw significant volatiles present in the post-DPF exhaust stream when sampled at the tailpipe, at least 2 orders of magnitude higher than instruments that were removing volatiles.
Great. We have time for one more question from David Kittleson, so I will ask you to unmute.
Hear me?
Yep, you're quite faint, but we can hear you.
Okay. Very interesting talk. I think it should be remembered that whatever we say about sampling artifacts, if you do roadside measurements or on-road measurements, the nucleation mode particles, or particles below about 30 nanometers, are largely volatile in the real world. Probably 80 or 90% of the material in that size range is volatile. So whatever you're doing with tailpipe measurements, you have to remember what's out there, and what's out there in the small size is mainly volatile.
Yes, thank you very much for that. I did read quite a bit of your work while I was doing these studies. I don't have any experience myself at roadside measurements, but I did greatly enjoy a lot of the work that you did. So thank you.
Great, thanks so much, Stephen. I really appreciate that and all the commentary and questions that we had in that talk.